So this session is on vector control and vaccines. This is on malaria. The vector control is for mosquitoes, vaccines hopefully for humans, unless you've heard otherwise. And our first speaker is Avik. He's come all the way from IIT Bombay in India. Go ahead.
Good afternoon, everyone. So I'm Avik, and I'm actually a PhD candidate at the Indian Institute of Technology, Mumbai. And today I'm here to present a collaborative work. So I'm very much delighted and privileged that I'm presenting the work of the malaria working group here at the Indian Institute of Technology, Mumbai, which is supported by Bill and Melinda Gates Foundation. And I'm also grateful to our collaborators from Indian Council of Medical Research who have been highly instrumental in this. And I also acknowledge the financial support from both my from Minister of Education as well as Bill and Melinda Gates. So the title is very long, as you can see, that the Association of Malaria in Northeast India with Land Use Patterns, Meteorology and Backward Communities. So yeah. So before I proceed, we actually attained independence in 1947, and we had malaria back then also. If you can see here, like around 1960s, we had this resistance which happened. Like the green line is showing the cases in millions, while the purple line is showing the deaths in thousands. And we had the resistance to DDT, and there was like 6.4 million cases in 1974. So the government of India, they implemented various intervention strategies throughout the years. I'll fast forward your attention to 2014 because in the last few decades, malaria is declining in India as far as it is reported. And in 2014, for both cases and deaths, there was a sudden spike. And the government actually implemented this national framework for malaria elimination, a part of the work which I showed yesterday in my poster presentation. And there the government addressed some of the key issues which were raised due to this outbreak. Now, as you can see here, like this is from 2018 data. And as you can see here, like throughout the years, in the last two decades, the same areas are consistently, contributing the maximum number of malaria cases. For example, in the central part of the country, and for example, in the northeastern part. And these are the clusters, like the significant clusters which were identified the JETIS ORD statistic. And then also the Plasmodium falciparum, like malaria is caused by both vivax and falciparum, majorly in India. So falciparum is the one which is causing the maximum cases in these two parts. Now, one of the part which is of highly interest is this part. This little part, this state is very small state in size, but it is very, very beautiful. One of the most pristine. It has one of the most pristine environments with lots of forest and very beautiful sceneries. And that state is actually Tripura. So what happened here, like in 2016, if you see, this map is showing the different areas where API of greater than 15 were reported, and the maximum number of such instances were around inside this red circle, which is actually the area of Tripura. And we found that there's a clustering in only few primary healthcare centers. And while the 30% tribes, these areas are home to indigenous communities, which are also known as tribes. And these are the ones which are contributing like 99% of the cases. So I will bring 2 years back and I will just show this, like in one of the community survey, which was conducted in 2014, when the country actually saw very increased outbreaks as well as deaths. Majority of the people who were having malaria, they were employed in jhum cultivation. Now, what is jhum cultivation? It's actually also known as slash and burn cultivation. Like you will have forest. These are typical evergreen forests, which are also rainforest, which are also found in Africa as well as Amazon basin. So what these people do, these indigenous people do, they clear the forest and they burn it. Then they wait for a few months and they start growing crops on it. And amidst that, they also stay. Like you see this hut, they stay, and these are generally the males which go like these are located at like an elevation of greater than 2000 meters above the sea level. And oh, sorry. Yeah. So, and this process is repeated every year. Like they go to a new patch of land and they do the same thing. So some images, like if you see the burning of forests which have been burned, and then the women are particularly employed in collecting the firewoods because these people do not have the conventional gas or gasoline or electricity. So they go to the forest and they collect. And interestingly, this is one of the huts which are located like at very highly elevated places. And if you see that the man in the person who's working there, he's actually bare chested, like he doesn't have clothes. And these are the roads which are actually there because it is not developed. First of all, there are muddy roads, and there are after rainfall, lots of water is stored there. So based on our surveys, we found that what the people do, they think that by using smoke, they can actually deter the mosquitoes away from their homes. And additionally, what happens is like they do not sleep covered, like they do not wear proper clothes, and they also keep their cattle outside their house, which creates a ideal secondary host. And there's also lack of knowledge. So we actually employed a GPS tracker, like global positioning system tracker, in one of the people who were employed in the Jhum cultivation. And what we found is like, this is the village hut, like this is the place where they are residing, and they are following this yellow line inside the forest. And inside this yellow line, we also did this this mosquito analysis, like what are the major subspecies of mosquito. Like in rest of the country, we see Anopheles culifaces or the Stephensii in the urban areas. But here we see the highly potent Anopheles biami, and you can see that the density is very high for some of the days. So we actually knew that we were of the feeling that, okay, Jhum cultivation is one of the most important determinants. So we wanted to do a modeling. And for that, we wanted to identify the areas under the Jhum cultivation. So we relied on the satellite data. We created the polygons and we mapped it for the entire state. Now, and we also performed a modeling analysis where we took some predictor variables like the land, which covered the land cover usage, like forest, cropland, shrublands, rubber plantations, as well as Jhum. And we also had some climatic variables and also about community. And the response variables were annual malaria cases and annual parasite incidences. Now, annual parasite incidences is nothing but the cases, reported cases divided by the population under surveillance. And it is normalized for every 1,000 people. Like it is a common indicator which is used in India for identifying the transmission regions. And we plotted like Tripura, the state of Tripura has 8 districts. And we plotted this map. The green part is actually, the green box is showing the response variables. And if you look at this, the 2 of the districts, they do not have any malaria cases and any API, hence any API. And these 2 districts have, very high land area under urban settlements. And these are like West District and Sepajijala District. And so our interest is like to get an idea, like how the variables are distributed, when the annual parasite incidence is greater than 0. And we find that, with the increase in the forested area, the annual parasite incidence is increasing linearly. In respect to Jhum, it is very much, it's not linear, but it's going like it has a polynomial curves, which we cannot explain by simply visualization. And we also see that for croplands, urban settlements, the API is decreasing with an increase in croplands and even rubber plantations. Now, so this map is actually showing, here, if you see that these are the different blocks, the lighter shaded are the different blocks, and the darker shade are the districts. Now, districts are actually divided into blocks, and the colors, the red color is showing the number of cases, the highest number of cases, which is like greater than 100. And the gray color is showing the Jhum cultivated area. And we do see from the spatial visualization that there is some association between this. When it comes to croplands, the croplands are majorly concentrated in the upper two districts where the cases are very low. So there is no. And we also observe that there is high multicollinearity among the predictor variables, which is expected. So we had to deal with that also. Now, before I proceed into the modeling, I actually wanted to show this result also, which we also additionally did a household survey. We went into two of the blocks, like the smaller blocks, and we performed the bivalent rapid diagnostic tests. And where we found that, if you look at the red colored Jhumia numbers, the 155, 38, 139, these are the ones which are having the higher malaria prevalences. Interestingly, malaria can be both symptomatic as well as asymptomatic. And this was a very preliminary analysis that we did back then. And we are following it up with a longitudinal survey also right now, which is going on for like 4 years. And asymptomatic, there is a true asymptomatic burden, which is also there, which is like undetected. And again, the Jhum, it's more prevalent in Jhum families, people who are practicing Jhum cultivation. So then what we did, we had the data from 78 blocks, like across the 8 districts. It was an ecological analysis, like this modeling part. And we had 2 response variables. So for the cases, we used the zero inflated Poisson model. And for the API, we use the zero inflated Gaussian, because Poisson model is for integers, like it works better when there are integers, and it rounds off the decimals to integers. And why we use the zero inflated model? It's because we had like 41% zero cases. Like in 35 blocks, we did not have any malaria transmission. And since there was like high multicollinearity, we used 3 regularization functions, lasso, ridge, and elastic net. And the idea was like, to have a better fit and to have a better calibration. Now, we had lots of options to model, and I'm going to show 2 of the models, 2 of the plots. This one is from the zero inflated Gaussian model, where we are taking the annual parasite incidence as the response variable. And the solid line is actually the actual API, whereas the dashed line is actually the estimated API. And if you see that there is no good fit here, like if you see because for most of the low transmission blocks, we are seeing that there's a good fit. But for the high transmission districts of the blocks, we are not seeing a good fit. Then we also did this, we used the malaria cases and we used the zero inflated Poisson. And we see that, in the case of when we are using the elastic net function for regularization, we see that there is a good heterogeneity, like there is good convergence and there is also good fit in the high transmission districts as well. So, and also statistically, if we see that elastic net is actually proving to be the best, like the mean squared error is the least, as well as the alkalic information criteria, as well as the BIC is also the least. And from the model, we ranked the predictors and we found that the Jhum lands are the most significant predictor, which are followed by scrublands. Now the scrublands are essentially Jhum lands, but they have been left as it is, like no more cultivation is there. And we also see that there is a minority influence, like it is more in the minorities. So additionally, we also conducted this cross-sectional survey focusing on the interventions, like what is the ideal intervention then? But the problem is that there are finch vectors present, which are mainly found in forest. And the biting is outdoors. It's not indoor, inside the house. Since the biting is outside, and it is also before bedtime, it does not follow a particular time, like during the night. So the common, intervention methods which are used, like the LLINs, the insecticidal nets, as well as the indoor residual spraying, they are not effective. So eventually we have to come up with a new intervention where we can use it for the better mitigation. So To summarize, we find that Jhum is a significant variable, and the village which are proximal to forested lands, they are the one which are strongly determinants of the malaria higher cases. And there is also a need for additional tailored interventions for the high transmission districts. Now, few interventions that which we have tested, and especially the people at the Indian Council of Medical Research, is like capacity building. We have started training the village like a lot of the people who are living at the hilly tops, they do come down to get some common source of food, to get food and other essential, daily life commodities. So we have started like training them, identifying them, training them, and recruiting them so that they go up and they raise the awareness and spread the awareness about this. And we are also in process of ideating a app-assisted real-time surveillance. And as I mentioned, that the ongoing work is involving a longitudinal study on the usage of interventions about their compliances, as well as estimating the true asymptomatic burden. Thank you.
Thank you, Avik. Any questions? I have one. So you had you had a slide that said there's a difference between Jhumland and cropland.
Yeah.
What is the difference between the two?
So Jhumland is essentially practiced in the areas, in the blocks or the districts where marginalized communities are more, like the backward communities are more. Croplands are the areas where like the people are living in the urban settlements, people in the urban areas, they are going, and these are at low elevated regions, but Jhumlands are at high elevated regions. Okay. Thank you, sir.
All right. Let's thank Avik again. And our next speaker is Charlene. Charlene comes to us from the University of Dashang in Cameroon. Am I saying that right? Dashang? Yes. And Isipe in Kenya. And she's going to talk to us about microsporidia.
So today I'm presenting on microsporidia. It's a fungi that is being found in the mosquito, and then when the mosquito is infected, he cannot transmit plasmodium to the human. So here we are modeling to see how we can use this microsporidia for vector population replacement and malaria control. So as we all know, malaria has always been a global health priority. And then since 2000, there has been a strategy that has been implemented, such as the use of indoor residual spray, insecticide-treated nets, preventing drugs. But now the issue is we are observing that since 2015, there is a resurgence in the number of malaria cases. These are like statistics from 3 sources: World Health Organization, Malaria for Medicine Ventures, and then now it's really like a threat for in malaria control. So there is need for innovative malaria strategies. And then microsporidia, not just innovative, but also bio-based control strategies. Now microsporidia, which is naturally found in the mosquito, has been shown to block the development of the plasmodium in the mosquito. If we know about the biology, normally when the mosquito is infected, he got the gamete. We have the gamete that develop into a kinete, then oocyst and sporozoite. And the mosquito is infected when he has the sporozoite. But now when the mosquito is infected with microsporidia, the development is impaired at the level of the oocyst. It doesn't go further. So the mosquito will not transmit to the human. And then what's so interesting, it's first of all, it's found in the main vector in Africa. We have Arabensis, Funestus, and Coluti. It's also transmitted vertically from the mother to the offspring, which are transmission varying from 45 to 100%. It's also transmitted horizontally through mating or copulation from the female to the male and from the male to the female. From the male to the female, it's around 56%, and from the female to the male, around 33%. It's also, it doesn't have significant effect on the fitness. So it's really very good in terms of, we hope it could sustain itself in the mosquito. So to analyze whether it's possible to increase that prevalence, in the mosquito population, we are building a model. We choose to build a system dynamic model. Why? Because it's really highly integrated. It allows us to take into account the main components that are really key in understanding the dynamics of malaria, human mosquitoes, and microsporidia. So here we will build the model, we will do calibration, we'll do a sensitive and scenario analysis, we will analyze the climate suitability, and then we will provide recommendation. So here, when we talk about the system dynamic model, like the main component, we have the humans, we have the mosquitoes. Here, we decided also to consider the integrated strategy. So in addition to microsporidia, we consider the possibility of using still ITNS, the insecticide treated nest, the indoor residual spray. But now the main component, like for the human part, we will consider susceptible, infected, and recover. For the environmental factor, we'll include the effect of temperature, rainfall, and humidity, and the carrying capacity of the mosquito. We consider as I said, the integrated strategy, indoor residual spray, environmental management measures like larvicides, and the mosquito is distributed in many. We have the gender, we consider male and female because it's really important to describe the transmission, male to female and female to male. We consider the age from 0 to 40 days. We consider the mating, which is also key in describing the horizontal transmission, because here we consider female a unique mating for female. We also consider the MB intensity, which is also key because we consider that if the mosquito has a low density, the infection can be lost from one generation to the next. And then we also consider the division in terms of plasmodium. We have negative, we have those at the stage of gametocyte, oocyte, and sporozoites. So the model, the system dynamic model is being built using the Stellar Architect software. Here, this is how it looks inside the model. Here you can see like most of the components. It has really a lot of variables, but then behind we describe all the variables and we describe the differential equation that are associated within the relationship. And then after we build the model, we proceed with the calibration. Data was collected in Ahero, which is a region in Kenya, available from July 13 to December 27. Then we proceed calibrated in terms of the prevalence of microsporidia in the mosquito population, and also the malaria prevalence in that region. And then for the statistic of fit, we analyze based on the root mean square percentage and the t-bias. We consider the both of them because here our model wasn't able to replicate the daily fluctuation, but we were able to replicate the overall trend, which is really good because our objective is not to replicate the daily, which can have, because there is a lot of error in the daily collection of mosquitoes. So now, in terms of like, after performing the analysis, we got many results. For instance, here, we saw like the strain in terms of like, if we decide we want to use this, we want to release mosquito to increase the number of infected mosquitoes. The first thing, what is important is the strain, because the strain determines what is the vertical transmission rate, what is the horizontal transmission rate. Because here we see that depending on those factors, we have an outcome. If the vertical transmission rate and the horizontal transmission rates are high, the outcome in terms of prevalence will be high, or it will be low. So this is an important point to be considered when releasing the mosquitoes. We also have the importance of the density. So here we realize that if we have because we've assumed that we can have like 4 categories of density from low to mid, and mid to high. And then we consider, for instance, if you have a low infection, and then from this generation to the next generation, if you can lose, if there is like a part of the offspring that lose the infection, then there is possibility of extension if there is a huge proportion of the mosquitoes that have low density. So this is also a key factor to be considered for the release of MB-infected mosquitoes. And then we also observe, like, we try to predict, let's assume, okay, we release the mosquito, how will it impact the malaria prevalence? Here, first of all, what we see is, of course, as we expect, more mosquitoes that are infected, less transmission, so we have better results. So we tested in terms of the release frequency. In terms of the release frequency, the more continuous the release, the better the effect. We test in terms of the number, the higher the number, the better the effect, and we tested in terms of the duration. So here, what we see is, like I said, as expected, the more we release, the better it is, but it's not proportional. So here, in order to be able to guide the biologists, those who will be doing the release, we need more of it. We need a cost-effective analysis, because it's not like if you release 4 times, you don't have 4 times the effect in terms of malaria incidence reduction. So we need to evaluate also the cost. So, and then something else we realize is also that it's not like sustaining itself. You see, once we stop the release, there's this curve that is going up again. So it means that we will need like more than one release to be able to achieve the control. So, and then what we did is to try to see whether by integrating the strategy, we will be able to maintain the malaria incidence reduction. And we'll see that with more, if we combine it, we have like, we can sustain the reduction in malaria incidence, but now what we need to look at is like whether, because of the insecticide resistance, by increasing maybe the use of this insecticide, we will not like activate more the insecticide resistance, and it could reverse the effect. So this is a point we should analyze also. And from the model, we have this interface that you can use to be able, like it's accessible online. You can check, the release strategy is just about defining how many mosquitoes you want to release, when you want to release, in which month, and what is the duration, what is the proportion of male you want to release, and then you'll be able to simulate and see the results. So the only point is the model here has been calibrated to a particular region, the Ahero, where we had the data in Kenya. So then another important point was the temperature, the climatic variables. So we tried here to see how it will influence the strategy. Here for the first graph, we tried to grid the map of Kenya using 0.1 degree. We extracted 3 centroids. We run the model over each centroid to see how the prevalence varied. And we got like a use distribution in terms of malaria prevalence. We also analyzed the effect of temperature, humidity, and rainfall. We saw that temperature has the biggest effect, followed by precipitation and then humidity. But then we also what is ongoing now is like trying to analyze how, with the evolution of temperature, like how the climate change, like in terms of for the following years, how it will affect the prevalence in the mosquito. That will really be key, because if we have a region where we have a possibility of having a higher prevalence in measles, a possibility of high control, especially if it's a region that has a high prevalence of malaria. So finally, in terms of summary, what we did was building a model. We provided a web interface. We did some scenario analysis for recommendation. In terms of the key insight, we show the importance of having a strength with good vertical and horizontal transmission. It's important for the biologists also, before like going for the release test, the effect of the density, general density, average density in the mosquito. We also show that climate has really a strong effect in terms of like we need targeted interventions. We need to choose well in which region is viable or not. And then we also show this one of the results was like MB seems to easily propagate where there is low white mosquito abundance. So meaning that competition might be really important to be considered, competition between lab hair mosquitoes and mosquitoes that are from the field. And then next, we saw that MB alone cannot sustain malaria elimination, and there will be need of multiple release, and also integrated strategy like can sustain malaria elimination. And then finally, we saw that increasing that mosquitoes, yes, it contributes to malaria reduction, but now for the effectiveness, there is need of the cost effective to see how financially it's viable. And then, so in terms of limitation, we need more data, especially for the spatial analysis, considering how will be the transmission in terms of distribution of vectors in the fields and so on. And then we also, the work we did, considering integrated strategy, we did not include the already used baby level of ITN that is already done in the field. So this is something we can do to upgrade the model. The interface that was provided is only calibrated to the Ahero region. Yes, so and then as the next step, we need to do a cost-effective analysis to be able to guide the policymakers. Thank you so much for your attention. I would like to acknowledge my this is done part of the SynBioVector project being had in Isipe in Kenya. I would like to supervise to acknowledge the supervisor Matoyo Pedesini from the Millennium Institute. He's one of our collaborators, my supervisor Henry Todang and Jeremy. And then the Bill and Melinda Gates that funded the project, Open Philanthropy, Children, and GAD. Thank you so much for your attention.
Thank you, Charlene. Any questions? Yeah. Okay. Do you want to go first, Charlene?
Thank you, Charlene, for such a really interesting talk. I was curious to see that even 10% coverage with ITNs had such a dramatic effect on prolonging the impact of the MB. So I was curious whether you had tested the impact of ITNs without the MB in your model and whether that resulted in an effect that was consistent with, I guess, what we already know about people's experience with ITNs. This is what I put into limitation that we did not consider. For now, we did not consider how. For instance, I think in that region they might be using already the ITN. For now, we've not, when calibrating the model, we've not included this is maybe if the malaria prevalence is 20%. It's they're already having this coverage of ITN. So for now, I can say that this result can really be applicable. We need to go and see how is the use of the ITN and those things before now we are able to see. We need to calibrate also in relation to the ITN for this result to be valid. Yes, thank you.
Cool. Thanks for that talk. Really interesting. You mentioned how the strain and also the density of the microsporidia is really important for its transmission and persistence. What are the factors that influence the density of it? Is that something that's climate driven or something else?
Okay, for now, that one, they are still trying to understand in the lab because you see they collect the mosquito from the field, they screen if it's infected or if it's not infected. Then once they screen, they can now try to evaluate how is the density inside the mosquitoes. And then they see just when they take this mosquito, it's different from this one. So it's an analysis that is ongoing. They're still trying to understand what caused the variation.
We have time for one more question. Anyone? No? Okay, cool. Thank you. Thanks, Charlene.